there. All right, so it's 10:31. I am going to get started. I printed like a few of the Master the Mainframe 2019 flyers, so it came out really good. I'm gonna put it, right at the door. So if anyone wants to find out more details, I sent an email to all of you already, which is basically the same thing. This is just a printed version of that flyer. So I'm gonna post it here if I can find something to nail it. Yeah, close enough. Interesting. I'm right here in the Career and Pathway Office has a young topology workshop on the 23rd of October. And that is closely related to the MBTI, the personality type test. Did I mention the personality type test in this class?
Yeah.
Yeah. So that class, that seminar, okay, I can't read that far when I put on these glasses. So the young topology is actually what is underneath MBTI. So if you have done your test, for MBTI, and you want to gain a more in-depth understanding of, what it means, what is your, what they call your dominant function, what is your auxiliary function, and how that affects, how you learn and how you work, which is kind of important when you're planning for your career. That would be a nice workshop to go to. Because MBTI is kind of like this superficial version of the young psychology stuff. So the two are totally related. So that's kind of interesting. All right, so I'm gonna get rid of this stuff, and we can resume our lecture. Okay, so the lab that you have today, let me open up the lab first, because I think we covered some of the material for today's lab in the previous class. So what we'll do today is we'll get started with the lab just to take a look first, and then we'll talk about the concepts involved in the lab. So the order of introduction is slightly different compared to the usual, I'll lecture about the concepts and then you have to do the lab on your own. So let me change the date first, just so that we have the correct date. Today.
Is this recording?
Yes, it is recording. Yep. Thank you for checking. October, today is the 9th, so 1 week from today, it's the 16th, and it is due at the beginning of the lecture. I do this just so that people don't miss the lecture to get the homework done. And obviously, there are quite a few people who try to do that. They miss the lecture in order to get the lab done, and then they're behind again, right? I mean, that's not a winning strategy. All right, so the preview, I'm going to show you the preview of this lab. So the preview of this lab has two links. The first link is a link to a Google spreadsheet where you have to make a copy into your own Google Drive. Okay, so I hope most of you know how to do this. Okay, it's not too hard. It's just a little bit tricky. You have to make sure that you navigate to your drive. Okay, until it says my drive, and then navigate down again. If you just click copy, make a copy, it will try to make a copy in the folder, which is my folder, and that's not going to work. Okay, so you have to make a copy first. And what this link really is really just a spreadsheet where you have a number. Okay, this number is based on the last 4 digits of your student ID. Actually, your full student ID, mine has 000, so the zeros got truncated. But based on your student ID, it will generate your test case for this homework assignment. So it is unique to you. Okay. Not that different people may not end up with the same value, but it is very unlikely that they end up with the same value. Okay, so this is the test case that you have to deal with, and then the rest of the homework description. There's another link here. So what this link brings you to, Okay, let me right click and open it as a new tab, and it opens it all the way over here. It's a zip file. Okay, so the question is, okay, what is in the zip file? The zip file contains a folder, and within the folder is a code blocks project. Okay, so you will have to open it. I have the whole thing downloaded already, so I can show you what it looks like when you open it in CodeBlocks. So this is what it looks like when you open it in CodeBlocks. Okay, there's a main program. When you go into the sources, let me just kind of close this and restart the whole thing, because this way you can actually see what it looks like. Okay, no, I don't need to save anything. There we go. Close, close. No, I don't change that. All right. So to do this project, you have two main ways of doing it. You can either use the command line version of GCC, which some of you may be introduced to use because Mr. Fox, this is how Professor Fox likes to do it. Or you can use CodeBlocks. CodeBlocks is an IDE, or an integrated development environment, and it looks like this. Okay. So my version is kind of old. It's 16.01. I think the current version is 17.12. Okay. But you can use an older version. We don't need the latest and greatest in this case. I got my project already, saved. But if you don't, you go to the folder where it will unzip. The zip file is going to unzip into a folder called double1, and inside that folder is going to be a double1.cbp, which stands for CodeBlocks project. Now Windows annoyingly will hide the extension, so you will have to identify the project file by the icon if you have CodeBlocks installed. Okay, so the first thing you might need to do is to get CodeBlocks installed. We'll talk about that separately in just a little bit. So once you open it, it opens up, and I got some files opened already. Yours would look kind of empty because, you would have a blank project to begin with. So you want to open up the sources within the project's view. And in sources, there are 3 C files. These are not C++, which means you're not going to be able to use C out. Okay, and of all of these 3 files, this is the only one you need to pay attention to. The file name is exp10 exponent of 10 to 2. Okay, and that's where you need to put your code. So are we doing okay so far with the project thing? Okay, it's being recorded. Okay, so you don't have to write down all of this stuff. It is also described, at least a good portion of this is already described in the assignment description. Okay. All right, so we'll talk about what you need to do. Okay, there's one little thing that you also have to do is, from what people told me yesterday, the debugger setting is incorrect in the lab. In other words, when you go to settings and debugger, this part is not configured correctly. It will give you like a big red box instead of the correct path. Don't write this down. This only works in Linux. So if you're using Windows, it's not going to work. The recording from yesterday, from yesterday's lab, is correct. So once you get to the lab, the first thing you might want to do is to go to YouTube and watch the video recording of yesterday's lab, because that's what you need to go through to fix the configuration of CodeBlocks so that the debugger works. Okay. All right. So this is really just setting up the tools. Now the question is, well, okay, once we get here, what are we supposed to do? So before I talk about that, let's put a breakpoint here. If you click on the right-hand side of a line number, but not into this part here, it will set a breakpoint. You can click again to get rid of the breakpoint. A breakpoint is a construct for a debugger to pause execution once execution gets to that particular line. So right now the subroutine is empty. Okay, there's nothing inside the subroutine that I can put a breakpoint on. So the only place I can put a breakpoint on would be the end of the subroutine or the end of the function. And to run the program, do not use the green arrow, use the red one. So the red play button will start the debug process. You click on that, it will compile the program, it will change the perspective, it will ask you, do you want to save it? Yes, it's fine, okay? So eventually, execution should get to this one, and it is not getting there. And that's because I forgot to set one thing. I have to go to project and go to set programs arguments, and then go here and say -n, whatever number I'm supposed to work with. Let's say it's 3.45, E negative 40, okay? I'm just making this up, okay? You have to copy yours from the spreadsheet. So I click OK. Now I can actually debug the program. So we'll try again. Okay, so we run the whole thing, and you can see the yellow arrow on top of the stop sign. That tells you that program has paused execution on line 11 of this particular file. So once you are at a breakpoint, you can do all kinds of stuff. Yes?
So at the beginning of line 11, or does
correct. So when at a breakpoint, if the yellow arrow is pointing to a particular line, that line has not executed yet. So we are just about to execute that line. So we are at the end of the subroutine, but we haven't returned yet. Okay. So once you're at this point, okay, the program has paused execution. There are quite a few things you can do. Okay, you can go to any parameter or local variable, like pn in this case. Right-click on it, and you can watch it. Okay, watching means it will just open a window and it will display the content of pn, which is a pointer, like continuously. So it can be useful when you're debugging a program, because you can single step through the program and watch, how a particular variable is getting changed. So you can click on this one if you want to. Okay, so you can see that pn is a pointer. It points to a structure, and it does not really tell you what is inside the structure. So it's not really particularly helpful to watch pn. It might be more helpful to watch whatever pn is pointing to. Yeah, it doesn't show you all the details either. So we can watch a particular member, let's say Mantissa. So it will show you the Mantissa. But the thing is, this is persistent. Okay, so this window is persistent. It doesn't go away, which means you can keep an eye on certain members of a structure continuously as you debug a program. Okay. I personally do not like to watch things because it kind of clutters up the screen too much. So I personally just like to go to the command prompt here and use gdb command. Okay, so I can just say print whatever pn is pointing to, and in this case it prints the entire structure, which to me is a lot more helpful than having to print one member at a time. Is that okay? All right. All right, so this is kind of like the basics, of what is happening. But when you look at the structure, some of you in the back may not be able to see the whole thing because the font is kind of small. It says Mantissa is 345, not 3.45. But we talked about that on Monday, right? Because we want to limit ourselves to only use integer arithmetics. So that's why everything is basically, they're all integer types. So the Mantissa is 345. The exponent in base 10 is not what the number started off with. What was the number that I gave myself to solve? -40. Okay, so it's off by 2. That off by 2 is because the decimal point of the Mantissa is shifted twice already. So that's why the exponent of 10 has to compensate for the shifting of the decimal point. Is that okay? So your job is to turn exp10 into 0 and use whatever value of exp2 and Mantissa that you need to do so that the end result would still represent the same value. Is that okay? That's kind of what you need to do with this program. And it's also written in the assignment description itself. Okay, let me go back to the assignment description here. Nope, not that one. Right here. So the restriction is the Mantissa should end up as a value that has bit 63 set, meaning that bit 63 is a 1. Okay? So you have to make the Mantissa basically as large as you can without overflowing. I shouldn't say overflow, but without exceeding the largest value that you can represent using a 64-bit number. The exponent of 10 should be 0 because that's the whole purpose. Okay, we're converting a number from base 10 scientific notation to base 2 scientific notation. exp2 is going to be some negative value. Okay, so expect that to be about 3 times whatever the exponent of 10 was. So if the exponent of 10 was, like in this case, 40, then the exponent of 2 would be negative 120-ish. Okay, it might be 130. Okay, but that's kind of the ballpark of what you can expect. The value that v is representing should be preserved as much as possible, which means it may not be exactly the same, but it should be really, really close to it. So are we good so far with this? All right, cool. So you can read the rest, about this one. I would strongly discourage people from using, approaches like cout or printf or something like that to try to debug the program. Instead of doing that, use breakpoints and use the debugger. Okay, so you can actually look at the value at specific points of the execution of your code. Okay, so having said that, we'll go ahead and just start with this one. Okay, we'll try to do it by hand, at least a few steps, and then see what we can do about it. This is a picture that talks about arrays in one of my other classes. Okay, so this is what we want, and this is also what we want. No, I want this, and I want that. There we go. Okay, so these are the two windows that I want, because I want to show you, how to do this by hand. And I will also need a terminal, which is not this one. I need one that is a little bit bigger in size, which is this one. So I got all the components I need at this point. We'll go ahead and get started then. Okay, so what we have here is 345 times 10 to the power of negative 42 to begin with. And I want to get rid of the exponent of 10. In other words, I'm trying to turn the exponent of 10 from negative 42 to 0. Okay? So the first few steps are going to be pretty easy, because because what I can do is I can say, oh, okay, we can make, let's see. Oh, this is the opposite of that, isn't it? Okay. So one way to do this, okay, is to, in order to increase the exponent of 10, I have to subtract, I have to divide the mantissa by 10, okay? But you can see that the mantissa is not too big right now. It's only 345. If I were to divide it by 10 at this point, I will have an error that is kind of big, which is 5 divided by 34.5, which is not good. How do I minimize the error in the division? Okay, yep.
By a smaller number?
Well, I cannot change what I'm dividing it by because it has to be 10, because I have to adjust the power of 10. Yep.
You chip it away small bits at a time, like divide by 10, and see where you're at, bitwise, and then do it again.
That won't help. I can try to make the dividend in the division as large as I can. Okay? In other words, I can say, okay, so I'm just doing this first, and then you guys can tell me whether it is okay or not. Okay? This may or may not be the final answer, so I would not write this down. Just kind of focus on the idea. Okay? So at this point, I have just introduced a times 16, which changes the value being represented. That's not good. Okay? So what if I do this? What can I do with the power of 2 so that I can kind of cancel out the multiplication by 16? Negative 4. Thank you. Very good. Okay. So this is represented separately. This is represented by the member called exp2 in the structure. So it doesn't. So we are not actually calculating this at all. We are just representing it. Okay. This is also just being represented as exp10 in the structure, so we are not actually calculating 10 to the power of negative 42. This, on the other hand, we actually have to calculate, okay? So now we have a larger number. If I were to divide this by 10, the error would be much smaller compared to dividing 345 by 10. Does that make sense? Okay, let me write it out separately. 345 times 16 divided by 10 has a smaller error compared to 364 divided by 10 in terms of percentage. Does it make sense to you? Okay. But when I look at 345 times 16, it doesn't seem like I'm maxing out what a 64-bit integer can represent, right? I mean, that's like really small compared to 18 with 9 zeros after that. Actually, no, I take it back. It's 18 with 18 zeros after that, okay? This is not even close. 345 times 16 is not even close. So now the question is, how do I know when I can stop? In other words, I'm asking this question, okay? 345 times some power of 2, okay, such that 365 times 2 to the power of this particular p is just under the largest value a 64-bit unsigned integer can represent. I need to solve for this p. How do I solve for that p? Conceptually. I think this resembles one of the questions in the previous lab, right? So we can solve for this. We can use log. Okay, we can use log and solve for that. Yep.
Sorry, going back. How did we cancel out the 345 times 16 with a negative 4 exponent?
Because 16 is 2 to the power of 4, and 2 to the power of negative 4 is 16th. So when you multiply those two, you get 1, which means they cancel out each other. Yep. Okay. So to solve for this p, we can use log. Okay. But remember, in this homework assignment, we also don't want to use anything other than integer arithmetics, and log is not integer arithmetics. So how do we do it? Well, we're going to have to use a loop to do it. Okay. So the way we utilize a loop to do it, let me see if I still have my, yep, I still have that up here. So I'm going to use a spreadsheet to kind of represent what I need to do, okay? This is P. This is, so P can start with 0, okay? And this is 345 times 2 to the power of P. So I just need to say this is 345 times 2 to the power of whatever this p is, okay? Of course, in this case, it's just 345 because 2 to the power of 0 is just 1, right? And I can make the next row, this cell plus 1, but the equation on this side can remain exactly the same because it always refers to whatever cell is right to its left-hand side. So now I can extend this a little bit, okay? You probably want to work this out to, some relatively large row number, like 60 something, okay? Now remember, this is just an illustration. This is not how you want to do it, okay? Because you have to write all of this code in C and C++. This is just, the approach of doing it, okay? So we will keep going and, oops, no, okay. Okay, so we drag it down a little bit more. Not quite. And okay. So I think at some point we would have reached the number that we want. But how do we know? Well, you can kind of eyeball it, but it's better not to eyeball it, right? So what we want to do is to say, are we done? Okay? But how do we know whether we are done or not? We have to look at the value in column B and then we ask the question, if I multiply this value by 2 again, am I going to exceed the largest value that I can represent in a 64-bit unsigned integer? That's the question, okay? But how do I express that question as a mathematical equation? What do you think? Let me state the question again. I need to know whether a particular number in column B is, if I multiply that number by 2 again, that it would exceed what I can represent using a 64-bit unsigned integer. Okay, so, yep, go ahead.
So you use like the circuit we made for compare, right?
Okay.
So 2 to the 65 minus 1
Uh-huh.
times the number we have times.
Okay, so let me just try to express what I need to do here. My question is, okay, I have this number already. The question is, if I multiply this by 2 again, is that going to exceed the largest value that a 64-bit unsigned number can represent? So by the way, what is the largest value that a 64-bit unsigned number can represent?
2 to the power of 64 minus 1.
Yep, okay, very good. So 2 to the power of 64 minus 1. And I will use parentheses to clearly indicate that the minus 1 is not in the exponent portion. It is outside of the power. Okay. This looks pretty cool, right? I mean, we can just type this out, and use this as a comparison in C and C++. But there's one problem. If the left-hand side is already exceeding this much as a 64-bit number, it's not gonna, you cannot represent this quantity if it is already exceeding what a 64-bit number can represent. Does everybody understand the point? That this won't work, okay? So what do you do?
Well, I mean, my immediate thought was just less than or equal to. Just find out if you're going up to that.
Well, the thing is, I want to avoid having this multiplication by 2, because this is what is bumping this over, what a 64-bit unsigned can store. Yes?
Divide right side by 2.
Exactly. We'll divide both sides by 2. Okay. So that means we end up with just 360 in this case, okay? 365 times 2 to the power of p. And we're really just asking, is that greater than or equal to 2 to the power of 64, the whole thing minus 1? And if you want to be exact, okay, that, right? So now we guarantee that both sides can fit inside a 64-bit unsigned number, okay? Both the left-hand side and the right-hand side. So I can now compare safely without having to worry about, but if that side is exceeding this amount, it's gonna, the comparison won't work just because of the nature of a 64-bit number. Is that okay? So I'm going to use this, in my spreadsheet. So switching back to the spreadsheet, there we go. We ask the same question, okay? So this is the cool part of using a spreadsheet, is you can use it kind of like a scratch pad of testing the logic of your code. Okay, so without writing the code first, you express it in a spreadsheet and go like, okay, is this going to work? You can visualize the whole thing, you can check it, and you can modify a few things and then check it again. So now we can say, okay, the condition we want to test is whether this number, which is the entire left-hand side, is greater than, oops, why can't I type? Is greater than or equal to, okay, I'll put in exactly the same thing that we have in the other side. On the other side, is 2 to the power of 64, the whole thing minus 1, and then that entire thing divided by 2. Okay, I'm just typing in exactly the same thing, but in a way that the spreadsheet understands. False. Are you surprised that we are not done? No, I hope not, because 345 is, it will fit even within a 16-bit number. Okay, so what we do is we just replicate this thing, all the way down, and keep going. remember, the largest value that a 64-bit number can represent is 18 times 10 to the power of 18-ish, okay? So we are going to get up to here, and that should end, okay? There we go. Is that making any sense? Okay? So your program kind of has to do almost the same thing. You have to keep track of the power while you keep doubling the mantissa. Because column B is nothing more than just the mantissa itself. You're doubling the mantissa for each row. Is that okay? And then you're keeping track of how many times you have been doubling, because you're just for the exponent of 2, right? And column C is the condition. When column C is true, that means, oh, okay, row 57 is the last one that I want. The actual value that I want end up in the mantissa is going to be this amount. 1.24 blah, blah, blah times 10 to the power of 19. Are we doing okay so far with this approach? Yes? So we know how to find the largest mantissa that fits into a 64-bit unsigned integer before the division by 10. Are we good so far? Okay. Oh, by the way, if you are to implement C code to replicate what this particular spreadsheet is doing, what do you think is the construct that you need? I'll give you 3 choices, okay? A sequence of operations, okay, without any loops or conditional statements, a single conditional statement, or a loop. Yeah, it looks like a loop to me. Looks pretty repetitive, right? And do we know when we can get out of the loop? Yep. Okay. So this spreadsheet gives you all the basic ingredients that you need to set up a loop, to find the largest value of the mantissa so that you can divide it by 10 with minimal error. The idea is to make it as large as possible because we don't want error in the division. We want to minimize it. Are we good? Okay. All right. So we figure that it is 56, okay? Excuse me, it's 55. The power of 2 that we need is 55. So now we switch to another terminal, okay? Because I need to use a separate calculator to get to the exact amount, okay? So we go to BC, which stands for, it's a calculator, it's a command line calculator. It's really quite useful. So it's 364 times 2 to the power of what again? Was it 55? Okay. And it gives us this number. So, Control Shift C. So there's no need to copy this whole thing, okay? You just need to remember the steps, the procedure, and the rationale behind it, because otherwise you'll be writing a whole lot of 18, 19-digit numbers for no particular reason. Okay, so I switch back to this here, and I go back to this part, and now I can say, okay, we found out what this thing is. It is this thing times 2 to the power of 55 times 10 to the power of negative 42, because we haven't divided by 10 at all at this point, right? Times 2 to the power of negative 55. Is that okay? So if you just look at the 2 to the power of 55 and the 2 to the power of negative 55, they cancel each other. So we know that we are still representing exactly the same value, right? All we are doing is we are trying to maximize the dividend in an upcoming division so that we can maintain as much accuracy as possible. That's what we are doing at this point. So now we say, what exactly is this? Well, we know it is that. Yes, go ahead.
I think 54, right? Because 55 gives us true.
Well, let's check, okay? So one way is to check it, and we say, do we have 18 digits? Oops. Yeah, there we go. So we do have 18 digits with a 12, before or as being the most significant 2 digits. So this will fit within a 64-bit integer because the largest value is about 18 and then followed by 18 zeros. So this will fit. So I think the math is correct. I haven't messed up the math. Okay? Okay, but the rest we still have to copy. Okay, so I'm just doing the really lazy thing. And you don't have to copy this because it's getting recorded. Okay? So just kind of focus on the logic. Is that okay? Are we still doing okay with this math here on the third row? We good? Okay. So looking at this huge number, and I go like, yeah, that makes me feel comfortable when we divide it by 10. I know the error is going to be really small. Good. But if I only do integer division, the result is going to be biased. In other words, every single time I divide by 10, the error is always going to be negative. The value that I end up with is always less than what it is supposed to be. Because integer division has a built-in truncation to it. Is that okay? So I don't like biased error, because a biased error means it will only go in one direction and it's not going to cancel out itself. Okay, which means the actual result will be smaller and smaller compared to what it is supposed to be. So how do we do rounding? In other words, now don't copy this, because this is going to be, I have to make several modifications to this. Okay, so the idea is I want to divide this by 10 so that I can change the exponent of 10 by 1 so that this can go up by 1. Okay, that's the objective. But the problem is, if I just do a division by 10, it's going to truncate and it has an error that is biased. The error is very small, but it is biased. If I keep doing this like 40 something times or 50 something times, the biased error will add up and the end result is going to be significantly different from what it is supposed to be. So how do I make sure that it is not biased? This also relates to a question that you answer on Monday in that lab. So we have to do rounding. Okay? Because rounding means half of the values will be truncated, but the other half is going to be bigger. Okay? So if we do rounding, each time we do a division, sometimes it is less than, sometimes it's greater than. So even though there is still error involved, they go in both directions, and hopefully they will kind of cancel out. Is that making any sense? Okay? So, but how do we do rounding? Because the target of being rounded is this entire thing. Okay? The result of the division is what we want to round. But we don't want to do any type of floating point or double operations. We want to limit ourselves to only integer arithmetics. So how do we do it? This is also relating to one of the questions on Monday. Yes?
You
Add 5 to the numerator?
Yeah.
Yep, that's it. Very good. So what we need to do, and this is why I asked you not to write this down, because I will keep modifying it until I get what I need. Okay, so just to emphasize the whole thing, I will move this whole thing to the left a little bit because I know it's bumping over the screen. There we go. Are we good so far? Yes?
Yeah, so you wouldn't divide by one with 18 zeros behind it because you would lose all those numbers.
Correct.
You want to do smaller.
Yeah, so you want to increase the ratio between the numerator and the divisor. And this is the best we can do because we have to get rid of a power of 10, so we have to divide it by 10. Yep. All right. So this should work out, okay? Now, this is the other thing. Somebody actually copied a constant with all the commas into a C program, okay? What do you think is going to happen if you copy this whole thing and put it into a unsigned 64-bit integer constant? What do you think is the actual value of that constant? Okay, first of all, is the program going to compile? Yes, it will compile because a comma is actually a proper available C operator. Okay? The question is, what is actually going to end up in the constant? If you just say const x equals to blah, 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 the highlighted portion, what is the actual value in that x? Huh? It picks the last one. Very good, because it is a comma-separated expression, but it really is an operator. So the comma as an operator keeps the last item. The last item becomes the value of the entire comma-separated expression. So that constant would just end up as 960. Okay? So be very careful when you copy and paste the constants, especially from a spreadsheet, because a spreadsheet almost always, well, okay, I shouldn't say always, but most of the time will automatically use commas to separate digits by groups of 3, because that's how people like us like to read numbers. But comma is an actual operator in C and C++, so it is syntactically correct, but it is not going to do what you think the program should do. Okay? So that means if you want to copy and paste a constant, you have to get rid of all the commas first. And then somebody's going to say, but why do we use comma as an operator and we just keep the last value of that whole string of things? Why do you think that is the case? Nope, has nothing to do with arrays, because this is it's a single expression. You can use a comma to specify a sequence of operations, so you can actually avoid the use of statements in many cases if you use commas. Then you might say, but what about assignment statements? Well, in C and C++, assignment is an operator. It is not a statement. In other words, okay, I'm just going to give you some code like this, just so that you guys will start to frown again. Okay, you can do something like this. Okay, this whole thing has a value of 70. Okay, but it does accomplish all the assignment operations as well. Is that okay? Then you look at this and go like, well, where am I going to put this then? Anywhere an integer can be expected. This can be an argument that you pass to a function call. It can also be something that you compare to something else. Anywhere an integer is expected, this can go into that place with the side effect of changing 3 variables in the process. And it will give you 70 as the value of the comma-separated expression. You can write fairly cryptic code this way.
Job security, I guess.
Yep. I'm not sure whether I gave you the analogy in this class or not, that C and C++, or especially C itself, is like a motor with a saw blade welded onto it. Yeah, this is one of those things, yes. Yeah, the other class, I told the other class, it's like, but how do I control the speed of the saw blade? Well, if you need it low speed, plug it to 110. If you want it to spin faster, plug it into 220. Okay, so you have just learned one more feature in C and C++ that is kind of obscure, but it is important. Because when you copy and paste numbers with commas separating the digits, you can run into this problem. Yep.
So that still assigns A, B, and C?
Yes.
But then counts as the value 70?
Yes, the expression has the value of 70. But it has the side effect of changing A, B, and C accordingly, according to the assignment operations.
Right, yeah, okay.
Yep.
So what, is that ever useful in that?
Make compact code.
You can make super duper compact code where, where a normal person would use like statements and conditional statements. Given this and ternary operators and recursion, you can basically write what we consider as common code using while, do, without a do, while loops, conditional statements, and individual statements of assigning something. You can turn all of that into comma-separated expression, ternary operator, and recursion. Yes?
Is it the same way if you put it in parameters?
Yes, you can put this whole thing into as in the place of one argument, and it will just pass 70 to that parameter. It makes sense, but it is cryptic. Okay, so now that we can, are we good with the C syntax thing? So the bottom line is don't copy numbers that use commas to separate digits by chunks of 3. Okay, you just remove all those commas first before you copy and paste. That's the bottom line. Okay, so getting back to here, I'm taking the highlighted portion and pasting into my command line calculator just so that I can get the result. Okay, not too surprising, right? This is the result. Nope, I don't want that. I want to Control C over here and then paste it back here. Okay, so when I paste it back, that's the result. And guess what? We have just gotten a little bit closer to 0, being the exponent of 10. The question is, what do we do now?
The exact same thing we just did.
Exact same thing that we did, but which part? Because we did several things, so which step are we going back to? Exactly, okay? Because this number here is not as large as it can be anymore. Why is it not as large as it possibly can be anymore? Because we just divided it by 10. Does it make sense? Okay, so now you have a question, and I'll leave it up to you to decide what logic you want to use. So what do we multiply to? Okay, let me highlight it because it's just easier to highlight it. So the question is, what power of 2 do I multiply to this so that it is once again the largest value before we run out of space with a 64-bit unsigned integer? That's the question. You can do it by trial and error. Okay, that's the easiest approach. We just take this, copy, go to the spreadsheet, and just say, well, okay, now we are starting with this value. And of course, we have to change the other ones too. Oh, let's see.
Put it in the V1.
No, it doesn't refer to it. That's the problem. So we have to, because none of them, this one only refers to 3, 4, 5. So I don't have it set up to refer to a particular value. So this is just that times 2. I want to set this up so that it's easy to just copy and paste again. It doesn't change the meaning of the code. It's just a different way to structure it. Okay, there we go. All right. Can someone tell me how many times I have to multiply it by 2 before I get to a number that is, okay, if I multiply again by 2, it's going to exceed what we can represent in 64-bit? 3. This is the first time, second time, third time. Is that okay? It's 3 times because row 5 has this value that is barely making the exit condition true. So that is the last value that we can use. Is that okay? So once again, that loop that you had before is useful again. It's just that this time we don't have to go like 50-something iterations. 3 iterations, we're done. Because we just divided the number by 10, and you can see that 8 and 10 are pretty close, right? All right, so in terms of the math, now that we know that we have to multiply this whole thing by 8, so what we do is we'll just go ahead and copy this row, and this time we know that we have to multiply this by 2 to the power of 3, which means we have to adjust the power of 2 by 3 as well. So instead of 55, it is now negative 58. Instead of negative 55, it is now negative 58. And now it's time to just carry out this particular calculation. Okay, so we copy and paste it here, get the answer, copy from here, and paste it back here. Okay, and I'm just going to do it really step by step, right? Copy and paste. There we go. Okay, so next we can now do the division by 10 again, right? So the division by 10 is going to be about the same thing as we did last time. We have to first add 5 to the number being divided for rounding purposes, and then we divide that by 10. And if I have a division by 10 here, I would adjust the power of 10 by increasing it by 1. Okay? And then we just try to figure out what this is. Control C, go to my calculator, paste, Control copy, and paste over here. So now my exponent of 10 is negative 40. My exponent of 2 is negative 58. So are we good so far? Okay. This is just repetitive now, right? Because you can go to this step and go like, okay, next we have to figure out what power of 2 should I multiply to this number before it exceeds that amount, right? Most of the time it's 3, but occasionally it can be 4. Why? Because 8 is less than 10. Okay? If 8 is less than 10, that means if I keep dividing it by 10 but only compensate by 8 on the other side, it's going to run short at some point. Okay? So, you just have to be careful, and not fix it and say, oh, each time we'll just go ahead and change the power of 2 by 3. Nope, you have to test it. Sometimes it's 3, sometimes it's 4. You can use a conditional statement to figure out which one it is. There are several ways to do it. You can also use a loop, because by the time the loop exits, it's going to be right anyway. So you don't have to say, oh, okay, I have to find a constant to compare to decide whether it's going to be 3 or 4. You can just use a loop. So that part is entirely up to you to decide how you make the mantissa as large as possible. So you keep doing this, and then eventually the power of 10 will go to 0. And whatever is left in your mantissa, you have to be careful, because the last mantissa that you end up with is not going to have bit 63 being a 1. So you have to bump it up one last time to make sure that that requirement is met. So are we okay with this, with the logic of the program that you have to write? Okay. So let's talk about debugging the program a little bit, because someone is going to run into these problems in a program, okay? And that someone usually is myself. So I go back to code blocks, and I'll write some code, okay? So to reset it, this is in debug mode. So if you want to reset the debug mode and say I'm done debugging, just click stop debugger or shift F8, okay? And it wants to switch back to the other perspective. It doesn't really do much. I mean, it's up to you to decide how you want to do it. Okay, so I'm going to go here and introduce a really, really stupid loop here. Okay, and in the loop I have to do something, otherwise the compiler will optimize it out and go like, nope, you're not doing anything here. So we'll just go ahead and do something that is kind of stupid. Mantissa ++, okay? So do not copy my code. It is not what your program should have, okay? If I see anyone writing this code in his or her program, I'll just laugh. I will not tell you what is wrong with the code. And just to make this even stupider, I'll do that. Okay, so are we fairly convinced that this loop will never ever exit? Okay, just a while one will convince that, right? Should convince you of that. Okay, so let's just say that when I wrote this code, I felt so confident this code is going to work, and I did not even bother to put in a breakpoint. Okay, so I just go into the debug mode and go like, yeah. Oh wait, why is it not giving me the answer? It's stuck in the loop, right? Okay, so you got two choices here. You can either stop the entire execution of the program, and then you have to figure out why the program is not exiting, or you can go to debug, and you can go to break debugger. Okay, so what break debugger is going to do is it will basically just pause the execution. Even though you're actually in an infinite loop, it will just find a convenient place to stop and go like, oh, okay, you want me to stop. I'll stop. This is where I stopped. Now, this is really helpful because it will tell you that line 14 is very likely to be inside an infinite loop. Now, line 14 is not just, the infinite loop is not just line 14 for sure, okay? But it will tell you at least that line 14 is in the infinite loop. So to find out the scope of the infinite loop, like is it the inner loop that I'm stuck in, or is it the outer loop that I'm stuck in, you just need to single step, okay? So single stepping, in this class for this particular lab, single stepping is really just, it's not letting me. Okay, I can type here. Okay, there we go. So single stepping in this class, you can just use next line instead of step into or step out, okay? Step into and step out are good if you're debugging things that have subroutines involved. But if I'm not using subroutines, I can just use next line, which is F7. Okay, it really helps to remember some of the shortcut keys because it will really help you, move a lot faster. So F7 is what I need. So I press F7, it goes back to the beginning, the next one, like that. So I can now tell, what is the extent of the infinite loop. Okay. Now, if you say, but I want to keep an eye on the variables or the values of a member of a structure that is pointed to by Pn, okay, then you can use a watch expression. You can go to a debug, and you say watch. Okay, where is it? Is it here or is it somewhere else? Tools, nope. I thought it's in debug, but I could be wrong. Debugger windows, does it have watches? There we go. So I can add a watch window, and it maintained all the things that I have specified earlier. But this time, okay, so Mantissa is already here, which is kind of handy, because as I do F7 to single step, okay, I have to focus on the other part of the window first. There we go. So you can see how Mantissa is changing. And you can also see, that whatever is being changed is highlighted in a different color. Okay, so as you single step through and you have your watch window up, you just have to pay attention to the red line because that is telling you what just got changed. Okay, so these are all the tools that you can use in order to debug your program. Now, the watch expression doesn't have to be a member of a structure pointed to by a pointer. Doesn't have to be the structure itself. So if you look at star pn, there's a little symbol to tell you that, oh wait, there's more, okay, more details, okay, which is kind of cool. But in a watch expression, you can actually watch a general expression, okay, and that's why it's called a watch expression. In other words, you can do something like this, okay. You can say, I want to look at exp2 plus exp10. Now, why would you want to add these two together? I have absolutely no idea. Okay, but I'm just saying, if you want to watch a general expression, you can actually do that. Which is helpful because if it is the value of a particular expression from variables and members of a structure that you need to keep an eye on, watch that expression instead of the individual items. So that will give you, it can be a condition, okay? You can say, is the mantissa larger than or greater than or equal to a particular value? It can be an expression. So it will give you either 0 or non-zero as a result. So this is a really particularly useful tool for debugging. And I haven't used this much, so I cannot really tell you how to remove, but I would imagine right-clicking on a row and selecting delete will remove a row. Okay, so that's pretty easy to control what you're watching. Okay, if you watch too much stuff, just get rid of some of those. Do we have any questions about how to use the tool, how to use code blocks? No particular question? Cool. All right, so without any questions, I'm going to go back to the notes so that you guys know, where in the notes, on my website that I refer to these things. So let me go back to the right window. There we go. All right, so getting back to the modules, what I talked about today is actually in floating point number representation. And to be more specific, the topic that we need to know today is exactly 5.2.1. 5.2.1, if you read carefully and if you understand the concepts that is involved, would actually tell you about the structure of the code. Okay, you need a loop here, and then inside there's another loop, and it will even tell you what the conditions that you need to use to evaluate. Okay, is it time for me to exit the loop? Okay, but I intentionally did not make it very clear so that you have to kind of think about it a little bit in order to turn it into actual code. Is that okay? So we are up to this point in terms of the lecture. The next topic, since we got, well, let me check the time. I can't always trust the clock. Yeah, we got 15 minutes. Okay, so the next lab is really 5.2.2. I give you a base 10 scientific notation that has a positive exponent instead of a negative exponent of 10. So in that case, what do we do, right? But before we move on to 5.2.2, do we have any questions about 5.1.1 or what I just did, as an example over here in Mousepad? Do we have any questions here? No questions? Okay. Do you guys see how this relates to the previous two labs? Okay, because the previous two labs, even though they do use log and some of the other math functions, they are intended to give you an exposure of what we are dealing with. There are different ways of looking at the same thing. There are different ways of looking at a double or a scientific notation. Yep.
So why are we going straight to doubles rather than the first floating point number?
Like just a float?
Yeah, just a float. What was your reasoning behind that?
Okay, people don't use floats anymore. So float is F-L-O-A-T, is a type in C and C++. It is referring to the single precision floating point number format by IEEE. So float only has 32 bits, which means if you combine the mantissa, the exponent, and the sign bit, you only got 32 bits to play with. And as a result, the range is much smaller compared to a double. The precision is also way smaller compared to a double. And that's why people don't use that anymore, because now we have 64-bit architecture, and we can actually do double calculations in hardware. All the I-core from Intel can do that. So that's why we don't use floats anymore, because the hardware can do really fast double calculations. So there's no need to resort to float anymore. Your question, and then back to you. Yep. Okay.
We use the greater than or equal to in condition, right?
In the condition?
Yes, greater than equal to.
Okay, that's a very.
It would be better if we use just greater than.
Okay, so let's go back to the spreadsheet. So let's go back to the spreadsheet here. So the question is, how do we express this condition? This is only expressing a part of it, because remember, what we need to do is to add 5 to the column B value before we divide it by 10. This does not take the plus 5 into consideration. So we have to kind of make sure that adding 5 is not going to bump it over. So technically speaking, it is not minus 4, but it is actually, because we have to add 5 to it for the comparison. So that means this is actually a plus 4 instead of a minus 1.
My question was about deciding between greater than, equal to, and just greater.
It should be greater than or equal to. The reason why it is greater than or equal to is because if the number in column B equals to 2 to the power of 64 plus 4 divided by 2, the next time when you, let's see, how should I put it? Okay. So the plus 5 is not going to be here. The plus, okay, let me think about it a little bit. Okay, the minus 1 is here. The plus 5 should be outside. If it does equal 2. Okay, there we go. Okay, I think this is the correct version. Sorry about that. Okay, so let's say it equals 2. Okay, so let's say you have a value in column B that equals to exactly to this amount. Are we good? Yes? If it does equal to and you double it one more time, what do you end up with? It will be the maximum value minus 5. Because this one has a plus 5 built into it, which means, if you have column B being equal to this amount, then you have room for a double and a plus 5. Is that okay? So when it does equal to and you perform one more iteration, what's going to happen? Then you only have the plus 5 left, right? That's the only room left for you to do anything. And then you get out of this loop. What do we need to do before we divide it by 10? Plus 5, right? The moment you add 5 to it, it's going to go back to 0. Because you won't have enough digits to represent that value anymore. So that's why you only stay in the loop as long as the column B value is less than that quantity.
How about this previous condition?
Huh?
How about in previous condition we had over exceeding to 18 digit?
Mm-hmm.
What about that?
What about
We use this before this condition.
before?
Before this condition, yes.
Well, I'm not sure what you're.
We have over there greater than or equal.
Yes, it's still greater than or equal to. I just put the plus 5 here to make sure that I got room to add 5 to it. I'm not sure what you're asking.
Just I'm asking about the stage before this stage. We had another stage.
Another stage.
Yes.
In the spreadsheet or in the notepad?
And we apply. I'm not sure about multiply to 10 or divide by 10.
Are you referring to this
Yeah.
portion here?
No, previous one. It's 2 to the negative 55.
You mean this part? What about it?
The next one.
The next one.
Right.
Uh-huh. What about this one?
Okay. What condition did we have for this?
I used the wrong condition, but because the plus 5 is only going to affect the last 5 values, and this is not even close to the end of those the last 5 values, so it didn't affect the decision for this one. So the program did have a bug, when I came up with this number, but that bug did not affect this number because it's not even close to the end of the largest value. Okay? And there was a second question. Go ahead.
I was just wondering about like for the like the IEEE designation for a float rather than a double.
Yeah.
Is it just like perfectly scaled down? Like so, for example.
It's not. It is. So you can look up a float or single precision. So you look up IEEE single precision floating point, and Wikipedia has a pretty good page on it too. So I will refer to the Wikipedia page, and the format is like that. So you have 23 bits instead of 52 for the fractional part of the mantissa. You only got 8 bits instead of 11 for the exponent of 2. Now this is the biased version of the exponent. So with this one you have to subtract 127 from the unsigned value in green in order to get the actual exponent of 2. But it's going to be a lot smaller. The range of value they smaller, because the most negative value you can represent using this particular exponent is 2 to the power of negative 127. With a double, you can go all the way down to 2 to the power of negative 1023. So that, because that's an exponent, we are talking about a much larger range of value when it comes to the exponent. When it comes to precision, which is controlled by the red portion, a double has 52 bits to specify for accuracy purposes, and the float only has 23, and that's also a big change in terms of accuracy. Yep. Now 32-bit, floating point number like this one is a lot more friendly to a 32-bit architecture. So if your processor natively only knows how to do 32-bit integer addition, subtraction, and whatnot, it's better off with this one. But most newer architectures are 64-bit internally, so you are not saving anything by using a single precision anymore. Okay, so does that kind of help explain why we do not use single precision anymore? It was around when we have processors that can only do up to 32-bit integer arithmetics, but now that we have processors that can do 64-bit, really fast, there's no need to drop back to 32-bit. Yep.
Do you expect new data types in the coming years?
Probably not, because the major bump from 32 to 64-bit is not so much that we need to do 64-bit integer math, because you can spend twice the time and actually be able to use a 32-bit architecture to perform 64-bit integer arithmetics. So that's not really that big of a deal. It mostly has to do with the address space, because in a 32-bit architecture, the largest space or address space you can deal with is 4 gigs. And there was a time when people think, oh, we'll never run out of memory space if we have 4 gigabytes of address space. But we did run out. And that's one of the main reasons why we move on from 32-bit to 64-bit architecture. It's mostly because the address space. Yep. In terms of integer arithmetics, we can always make up by instead of doing a 1-clock operation, now we have a 2-clock operation, which is not too bad. But when it comes to address space, when you run up to that limit, you're done. I mean, there's no way to get around it. Yep. All right. So any other questions about what we need to do today in the lab? Now, you do have 1 week to work on it, so I would not try to rush it. Okay, so if you cannot get the whole thing working, if you can just get the one portion working, which is coming up with the largest mantissa before the division by 10, it's all good, okay, because you got some extra time to do it. So I would focus on the idea first. If you need to sit down and work out a different example, by following what I just did here, but just kind of do it by hand, just so that you get a sense of what needs to be done, that may be more beneficial than just sitting down and starting coding right away. Okay. All right. So don't forget to watch the video recording from yesterday's lab, because that will tell you how to configure code blocks to fix the debugger problem. Okay, because you will need that in order to debug in the lab. The video from yesterday's lab also will teach you how to install code blocks if you want to get it installed on your own PC or Mac or Linux in your desktop. It has versions available for all operating systems. Okay, any other questions before I let you guys take a break before we get to the lab at noon? Okay, so let's go take a short break and I'll see you guys at the lab.